Yeah, so let's start our conference with the first keynote. I'm really happy to have here Dr. Peter Kogge. He is currently a McCourtney Professor of Computer Science and Engineering at the University of Notre Dame in Indiana, but he worked very long for IBM, and he was even a fellow of IBM and a founder of a company called Emo Solutions, which is now named Lucata Incorporated. He is a fellow of the IEEE and the AAAS, and he has done a lot of pioneering things. So you might know Peter Kogge for his Kogge Stone adder, which he actually developed during his PhD thesis. But he has done many other projects which are very, very interesting and impressive. So he worked on the IOP, which was the world's second multi-threaded parallel processor, which finally flew on every space shuttle. He worked on the IBM 3838 array processor, which was for a time the fastest floating point machine marketed by IBM. And he worked on Execube, which was probably the world's first multi-core processor and first processor fabbed on a DRAM chip. And then in 2008, he led DARPA's Exascale Technology Study Group, which produced a report on technologies and architectures for exascale computing, which is highly cited. And his startup, Emo Solutions, has demonstrated the first scalable system that utilizes mobile threads. I think we'll hear about that more today, to attack large-scale big data and big graph problems. As you can imagine, Dr. Kogge has received a number of awards. I'm not going to name all of them. I'm focusing on the, to me at least, most prominent ones. So he was given the IEEE ACM Seymour Cray Award for High Performance Computer Engineering in 2012. He got the IEEE Charles Babbage Award for contributions to the evolution of massively parallel processing architectures in 2014. And he was named IEEE Computer Pioneer by the IEEE Computer Society, and that is their highest award that they grant. So I'm really happy to have Peter Kogge here for our keynote. He will talk about his uptake on the Cambrian explosion. The title of his talk is The Cambrian Explosion in Architecture. Are we there yet? Please, Dr. Kogge, the stage is yours.
Thank you. Can you hear me?
Very good.
And can you see me?
We can see you right now, not your presentation. Yeah.
Okay, I will do that. How about now?
Perfect.
Okay. Thank you. Well, this was a real pleasure to be asked to give the keynote here. It's very seldom that when you read the theme for a conference that it grabs you the way this one did, and so I'm very happy to be here, and I hope you find what I'm going to say interesting. Screen. There we go. I'm going to talk about this whole idea of Cambrian explosion and related to computer architecture. And along the way, I'm going to question, is there something in the way of us achieving it? I do think we're near an explosion, but I'm going to do some comparison to life forms, which I think you'll find interesting. I think we're still focused on the plant level, single cell / plant level of evolution, and we haven't quite reached the point that triggered the Cambrian explosion, and I'll go into that in more detail. I think there's I'll call a locality wall in the way of achieving it, and I'm going to suggest that to get beyond this locality wall, we introduce animals into our architecture, and I'll show an example that actually came out of the company I started. So I'm going to focus on highly parallel architectures rather than simply core architectures, because I think there's a lot of interesting things there. So anyway, this was the Golden Age paper that was referred to at the beginning. A really seminal paper that's worth reading if you haven't. Just as a summary, these are some observations from that paper. There was a bunch of things, I'm not going to read them off, but a bunch of things on the left that got us there, that Hennessy and Patterson both pointed out as being important. And also where we are now, things on the right, things like, you know, we've ended Dennard scaling, we're about to end Moore's law, and we're beginning to introduce some additional things like 3D stacking. So those are all things that come into play. And the challenges also, I got two sets of challenges here. One drawn from Hennessy and Patterson, which is 2018, I believe was this paper. They claim that the challenges to architecture were energy and power, managing dark silicon, the silicon that we can't use because of power on the chip, security, a variety of cache issues, and a gap between high-level languages and the underlying architecture. And I agree with all of these, and we'll see the locality issues are tightly bound in with these cache issues. Also, the 2008 report that I led, we came up with 4 challenges which are pretty good matches. The first was power, 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 and power, to stress its importance, and that, of course, has been proven true. Inadequate memory performance, programming to efficiently use massive parallelism. We talked at the time of potentially having to have a billion threads at the time, and we're now into the tens to hundreds of millions. So I think that's in fact a problem. The other problem we raised was reliability, but that seems to be out of control. So I'm not going to mention that too much right now. So the opportunities, Hennessy and Patterson said there were 4 opportunities to help us enter this golden age. The domain-specific languages, matching domain-specific architectures, open and modular ISAs, particularly RISC-V, and what they called agile hardware development, where you know, we mentioned FPGAs at the beginning, where as you develop a system, go from different levels of prototypes and you change the technology that you go there, you use enhanced tools to make the break between levels. And in fact, the processor I'm going to mention later that does this animal-like migration is in fact in an FPGA for exactly the reasons that they specified. So the question was, are we going to get to this golden age? Well, let me have a couple of definitions first. Architecture, if you look it up in the dictionary, architecture in general is the design of inhabitable structures. So what we're talking about, our inhabitants are computational threads. Those are the things that live in our machines and go about their lives doing things. Evolution then is changes in the characteristics of an organism. And the Cambrian explosion was when all the major animal phylum emerged. And I'm going to talk about parallel systems here when I talk about explosions and what have you. These are the 5 topics. I'm going to go through a little bit of evolutionary analogs. I'll then talk about a little bit about archaeology and evidence for this new wall. And then this idea of breaking the wall within animals, and then looking forward. And by the way, these are baby emus, and if you noticed, my original company was called Emu Solutions. And there's a story behind that I'll perhaps at a different time. So life form evolution. I'm going to talk about cells and organisms. And this is kind of the picture of the evolution of cells over time. The oldest cells appeared like 4 billion years ago. 2 billion years ago, there was a growth in the complexity of cells. We went from prokaryotes to eukaryotes. And then the difference, and these are the modern cells, these guys. And if I match those up to a modern core, computer core, these guys, the eukaryotes, had nucleuses to contain the DNA, which is the programming for the cell, and that kind of corresponds to program memory. They have well-defined organelles, and if you look at our cores, we've got function units, we've got memory hierarchies, and what have you. And they had these things called plasmodesmas, these little holes in the cell wall where stuff gets in and out of the cell, and those kind of correspond to basic I/O. So in a sense, a core kind of corresponds to a cell, at least in the evolutionary context I'm going to talk about. So the thesis was, at least our parallel systems, we have only plants. We haven't introduced animals yet. And if you look at about 600 million years ago, we made the transition between plants and animals. And this is what I'll dive into a little bit more. If you look at the literature about what caused the Cambrian explosion, the original common view was that it was caused by the growth in oxygen in the atmosphere. And this is a plot of oxygen versus time in the atmosphere. And this is supposedly where things really started to appear. And the common view was that this provided more energy for metabolization. And the problem with this is you don't need a whole lot of sophistication. You need more energy, but you don't need a whole lot of sophistication if all you're doing is grazing. And a more newer view was that what happened was there was a need to penetrate this microbial mat that covered the bottom of the C4, and the need to get through that mat led to a gradual rise of predators. And the rise of predators, skeletons, nervous systems, and all the like. And these are pictures of the kinds of animals that existed. This is the pre-Cambrian animals. They were kind of just blobs, mostly grazers, no back structure, no sensors, and what have you. And after this point, you get things with eyes, with muscles, that can move around with backbones and shells and stuff like that. So the new view is that these animals appeared, and their complexity was driven by the need to feed and to be a predator of some sort. So if you look then at the types of tissues in these organisms, plants had three simple kinds of tissues. Ground, dermal, and vascular. And animals, this transition meant that we came to tissues that had much more complex organizations of cells. Particularly these muscle and nervous tissues are not things that occurred in any kind of form over here on the plants. So these were the ability to form these kinds of tissues was important. And so now I'm going to kind of go through in terms of architecture and try to match that up to these kinds of things so we can get to a discussion point. So what drives great changes in computing? Well, if you look back in time, and this is what I'll show you, when the evolution of our inhabitants, these threads that are executing various applications, hit some sort of an environmental wall caused by the architecture. And there were three walls. There's two walls in the past that are famous, and I'm saying I believe there's a third one now. First wall was the mid-90s, and this was the infamous memory wall. Second one was 2004, the power wall. And the third wall, I think, was what's occurred now, and I'm calling this the locality wall. And this is largely due to the apps, again, our inhabitants, that have that are memory intensive in ways that are different than prior memory intensive apps, and they're not addressed by the classical architectures. So to date, again, I'm talking about parallel systems here. To date, in the evolution of parallel architectures, we started out in the 1990s to 2004 in what I'll call the slime mold area. These slime mold are colonies of simple independent cells that don't really interact with each other than just kind of being there. And these are arrays of simple single course processors that talk to each other by MPI or something like that through simple I/O. Then after 2004, we went into the fungi era where we have more complex single cell types. There's still multicellular organisms, but now there's more complex types there. And these are basically arrays of homogeneous multi-core processors. So we've got a lot of multi-cell, multi-core nodes that are all connected together, still in a fairly loose connection. Then where we are today is the MOS era. And these are where we've had the emergence of multiple cell types. And these are heterogeneous processors, hybrid processing, smart network controllers, and the like. And that's where I believe we are now. So just to kind of go back a little bit about what drove this, back in the slime mold area, the beginning in prehistory, this is late 80s, early 90s when we first got basic parallel systems, the applications were things like 3D mesh simulations, physics problems that could be expressed in multiple dimensions, and you match the application the way we coded it and the architectures to match those. So the issue there was simply getting more than one core, and this was the era where cores were multiple chips or maybe even multiple boards if you go back to Cray style machines. And the solution was parallel microprocessors, multi-dimensional fixed topologies, maybe 3D topologies, and using Moore's law to scale up the clock. The second, we did this, and then we hit this memory wall where the application of interest, at least in terms of high performance computing, ended up being solving linear algebra problems like AX equals B, where A is a big dense matrix. And this is in fact what the top 500 benchmark benchmark is. Back in the early 90s was memory bandwidth, and detail on this in a second. And the solution was to scale up the clock and increase the ILP of the cores. When we finally entered the fungi era in about 2004, we're still solving the same problem, dense matrices, but we hit a problem of socket power, and our solution there was flatten the clocks. And so these are some pretty major changes. Flatten the clocks, simpler caches, and higher intensities on the processors, and the introduction of some GPUs. Last week, if you will, the application was still with this dense thing, but we began to hit power efficiency problems. And the solution here is accelerators, hybrid nodes, multi-level memories, bigger caches, and so on. And then yesterday, if you will, we began to hit sparsity issues. One of the things that's been noted in the top 500 is that HP linpack, the dense AX equal B dense, doesn't really correspond to the way most problems are written these days, or solved these days. So the HP, the high performance conjugate gradient application came into play, where you're solving the same thing, AX equals B, but you're solving it with A being a very sparse matrix. And the issue here is we become bandwidth bound and with horrible operation efficiencies. And our solution was basically more of the same. And that leads us to today, where I think we have a much more severe extension of the sparsity problem that I'll call the locality problem. And that's because we're now, our inhabitants now are machine learning problems, data analytics, and things like that, where we have a lot of persistent data, pervasive non-locality of data versus where the cores are, and massive numbers of remote operations. And we haven't really come up with a community accepted solution yet. So the memory wall, just to go back quickly, this was where over time Memory performance was increasing at 7% a year. CPU performance was increasing at 60% a year. And breaking this wall, we used the extra transistors we had for bigger caches. And we could do that because the applications had plenty of locality. And just as an example, to solve AX equal B, where A is large, dense matrix, this has tremendous temporal locality. In fact, if you can read a patch of, say, n by n, a chunk out of A into a cache on your core, it takes you order n squared operations to read it, order n cubed operations that you can perform on this patch. And that ratio means if I work on increasing my floating point potential with a big enough cache, I don't care how slow the memory is. I can overcome it to do these kinds of operations. The power wall was similar. Around 2004, we began. These are the voltage used by different styles of CMOS chips. And somewhere around 2004, you see they all start to flatten. And this flattening increased the power density, the power per square millimeter on the chip. So bigger chips meant more logic to dissipate more power. And the result here in this chart, this is power versus time. Around 2004, we were hitting about 120 watts a chip. And at this point, cooling became uneconomical. So we had to do something. And the result was, as I said, flatten the clock. And this is a chart of clock versus time. And you can see 2004, the clock went flat. Go to multi-core, simpler cores, increase a SIMD style parallelism to put more flops with less logic on it. And the side effect, we needed more bandwidth. And the solution that the world decided on was, again, bigger caches. So here's some statistics. This is the growth in cache per chip. And this is aggregate cache size in megabytes versus time. And the compound annual growth rate is 38% on this. So each year, the amount of cache has been growing at 38% or better through this period of time. Likewise, the core count, as I said, we entered this era multi-core starting 2004, and the compound growth rate for the cores in this era is 32%, so that's less than the cache rate. So the size of the cache is going up faster than the number of cores. And the memory bandwidth per chip, however, is only growing up by like 10% a year. So this is slightly better than what we had back in the mid-90s, but it's still a lot less than everything else. So where we are today is our nodes, our basic organism, if you will, is pretty diverse. We've got several different kinds of processors. We got GPUs, we've got general purpose cores, we got several different kinds of interfaces to tie different kinds of things together, and we have several different kinds of memory, DDR, HBM for intermediate memory, GDDR perhaps for the GPUs, and so on, and smart network chips. So we've got different kinds of cells and different kinds of and often very complex. The processors themselves are multi-cell organisms. So in a logical view, though, we have this huge multi-level memory view where we've got multi-level caches, intermediate memories, scratch pads, and off-chip memories and what have you. And the issue with this is if you're a core trying to do something, nothing is uniform when you go trying to make a reference. A reference that you make now may be handled entirely different than when you make it a couple seconds from now. So the other thing that's, again, what Hennessy and Patterson used as evidence that we're entering a golden age of evolution, we are beginning to look at non-traditional processors and systems. So these are various kinds of things. The NVIDIA, for example, has systems of thousands of GPUs and not much in the way of conventional processing. The Google, they have systems with thousands of tensor processor units. In fact, they've just introduced a new one, TPU4, and these guys are all based around hardware-based 100 by 100 matrix vector products in hardware in low precision. And then finally, we've also got things like wafer scale integration, where we have hundreds of thousands of cores, and upwards of 1 trillion transistors. This is on a wafer scale chip. So all of these are clearly non-traditional kinds of beasts, and all different. And so if you also look at memories and things processing in or near memory, we now have all kinds of intermediate memories and scratch pads appearing in systems. We've got 3D stacks mounted on substrate interposers next to a chip, processor chip, to give bigger bandwidth at lower energy. And we've got all kinds of compute and memory kinds of things. We're using, for example, resistive RRAM to build into a memory structure over here, basically embedded linear algebra capability. Low precision, but where you can do matrix vector products directly in the memory system. So those, again, are all non-traditional. And last but not least, we're also beginning to look at chips and that look more like neurons than the normal kind of cells that we've been doing so far. So this is a human neuron, the key parts of a human neuron. There's a processor part of the cell body. There's dendrites, which receive signals. The axon is this big I/O cable that can be up to 1 meter long. And synapses are the ends here where you can get signals from other neurons. And in the brain, there are neurons with up to 200,000 of these synapses. So they can get information from a huge number of other neurons. And this is a collection of modern chips that are exploring this kind of cell design. And luckily, this is something that we're going to hear tomorrow's keynote. I'm looking forward to that. We're going to hear more about this whole area and what makes it so much different from today's classical computing. So evidence of a new wall. This was a chart that I put together a couple of years ago, and it's kind of motivated a lot of the work I've been doing and I've been having my grad students work on. This is a chart where I've been tracking a lot of these, the top 500. There's a website now that's 25 years old of data of literally hundreds of systems and how they perform. There's an equivalent set of websites on HPCG and on the Graph 500, which I'm actually on the committee for the Graph 500 for breadth first search for very large graphs and doing graph operations on these things. And so what I did was I took all this data and I looked at how the performance was as a function of the number. I have domains down here, but you can think of this as MPI ranks or individual nodes. And I looked at the performance of systems that had only one node in them. And whatever those performance was, I counted that as a unit performance. And then for that benchmark, I took the best performance reported for systems at other numbers of nodes. And what was striking that really got to me was that they all exhibited this really bizarre behavior. You go from one node to even a small number of nodes, and you lose performance. The machine gets slower, and not slower by a little bit, but slower by 1 or 2 orders of magnitude. So you give up a huge amount of performance when you try to go into a multi-domain range. Now, very often, all of these guys get into regions that you look at out here. This has really, all of these guys have really good scaling curves. They look like they're scaling nicely. Key thing, though, is you've thrown away an order of magnitude or better in terms of performance from what might have been a perfect scaling if they had gone up perfectly. So that's kind of the first bit of there's something funny happening here. So my thesis is this is a locality problem. And locality, again in the dictionary, is a place occupied by certain people or is the scene of particular activities. And in computer science, locality is the tendency of a processor to access the same data repeatedly over a short period of time. And there's three kinds of locality: temporal, reference the same data; spatial, reference nearby data; and physical locality, reference data on the same physical construct, kind of a generalization of spatial locality. And this latter one in particular, I think, is where things are beginning to become important. The second thing I'm going to use to look at evidence of this wall is the now well used Roofline model. And the Roofline model is a measure of useful operations per second for whatever app you're looking at versus operational intensity, where this operational intensity is defined as the operations performed over the memory transfers and divided by the amount of memory transferred. In other words, if you took the flops that they do and divided by how much memory you needed to get those flops, you'd get an intensity. So there's two parts to this curve. When you get an intensity that's high enough, the best you can do is you can do a lot of flops, for example, if flops is your measure. If the hardware is running at its peak and you're not limited by memory, so you get this flat line in terms of performance. Over here, you're memory bound. You don't have enough flops to keep the machine busy while you're referencing memory. So in higher intensities, you're here. Lower intensities, you're here. HPL, the AX equals B, dense is over here, way over here. And the operations I'm going to talk about are over here. And this ridge point is an important point. That's a part of the architecture of the ratio of its peak flops to its peak memory bandwidth. This is a chart of peak hardware intensity versus time. This over here is the flops per byte of memory bandwidth. And you can see it's been climbing exponentially. And for maximum efficiency today, we're at the 20 plus in terms of intensity, which means you read something from memory. In order to use the machine efficiently, you've got to find at least 20 odd flops to do. And if you want to think a little bit more about memory in terms of random accesses, if you talk about flops per access, where each access today you go out and you get 64 bytes or 128 bytes or what have you from memory. That curve looks like this for real machines. And the net takeaway for this today, if you want to use your machine at the peak maximum efficiency, for every memory access you make, you got to find 1,000 odd flops to do. And I've got similar charts for other kinds of measures other than flops. Excuse me. The causes for this locality, clearly there's branches that we get rid of through a lot of vector and SIMD stuff. Data irregularity, this is sparsity in data structures, and this is the killer for HPCG, for example, and sparse matrix operations. Data partitioning, though, is the killer when we get to these bigger systems, when you want to scale. And the communication in here overwhelms the computation. And I've had something go blank on the screen. Am I still audible? Anybody?
No.
Yes.
Okay.
Yes.
Good. Thank you.
Audio is perfect.
I just saw something go blank on the screen. I was worried I died. Okay. So these are some apps that we've looked at over time, and I mentioned a couple of them so far, and I'm going to mention a couple more very quickly, but not all. This is, again, if you look at time, this is peak flops as a function of time, and we've all seen this if you've looked at the top 500 data for big parallel systems. This is an exponential rise. And for the dense regular math, operations, they track very much the shape of the peak flops. We get 80–90% efficiency. And that rapid increase is driven by this Moore's law thing. We can grow the intensity, and if we grow the cache, we match. This was HPCG. HPCG is sparse, which kills the performance inside a core, but the data is partitionable nicely so that you can scale relatively well once you get beyond a single node and throwing away this overhead of performance. And what we've seen here is, unlike the dense matrix versions, the sparse matrix versions ended up being pretty flat. And the graph 500, the search of a big graph, is measured in not flops, but giga edges traversed per second. This is a sparse, irregular, and not very partitionable problem. And here we saw the same phenomenon of relatively slow growth over time, nowhere near what we see in the hardware. And so this implies that the flatness is bound by something else other than intensity, and it's memory bandwidth and interconnect here. And just this business of energy being important, this is a chart of these graph 500 operations versus the size of these irregular matrices that we have to deal with. And this is in terms of billions of edges. The green squares are reports of processors that were single nodes, and the blue squares are multi-node systems. And what you see, interestingly enough, is that the gigateps per watt, the power efficiency, dies as the problem size grows by the cube root of the number of edges. So if I have a problem that's 1,000 times bigger than my original problem, I should expect to see 1/10 the energy efficiency per edge that I saw before. These three guys up here are interesting. Those are cases where the whole matrix fit in the GPU memory. So that's an interesting side effect. There's an interesting paper that looked at big data analytics and looked at how they work inside our cores. So how well are our cores designed today for these architectures? And there's a lot of speculation that we do in cores. It doesn't work very well for these analytics. The CPIs that you expect, the Xeon, for example, at a CPI of a quarter, it's up to as bad as 3 for a lot of these things. Terrible. Execution ports, you got lots of execution units to use, very heavily underutilized, and we're very heavily memory bound on these things. So this is evidence that the cores aren't doing well. And so let me move up to then and look at the combination of cores in parallel systems. And I'll first look at SpMV, sparse matrix vector products. Here I've got a sparse matrix, I got a dense vector. I've got there's different ways that I can break the sparse matrix up and put it on different processors. Each of these little squares is some sort of a processor in a parallel combination. And when you look at these things, the sparsity makes the local computation memory bound, so you get poor utilization. And the increased concurrency increases the number of partial row accumulations, which have to be handled by I/O. And there's no single partitioning works forever. And if you look for everything, if you look at their intensity, this is down about 0.1 versus our hardware that I said is up at around 20. So this is a chart that one of my grad students put together of 4 different systems of the ratio of communication to computation within an SpMV. And in all of these things, and this is over a spectrum of about 30 matrices, the net result is they're almost all, doesn't matter what you do, you're over 1, which means, and in fact, very often you're up to hundreds or thousands. So it's 100 to 1,000 times worse the time you spend on communication versus the time you spend on computation. So what that means is we don't care about the cores. Net result is, if you look at the scaling curve, you get this massive loss that gets worse with scale. So machine learning, This is an application using stochastic gradient descent. There's a relatively famous algorithm here called Hogwild, which was one of the first algorithms to look at parallel machine learning using gradient descent. And it worked great up until about 10 threads, 10 cores, and then it died off just as we saw before. And improved algorithms, Hogwild++, for example, improved things, but again, we got this decaying behavior once we had too much parallelism. Firehose is a streaming benchmark from Sandia, where you have a series of packets that you want to bring in and analyze them through essentially a giant hash table and look for events. And the data that they recorded here has two variants, and in each variant, you get within a single node. You don't get very good scaling within a single node. You go from 1 to 7 cores, and you get a factor 2 performance increase. When you get to large parallel systems, you do get a good-looking curve, but it's an factor of like 60 below perfect scaling. So that doesn't work well either. And this thing has about 13 memory operations per datum that you have to process, and a lot of which are atomics. So these are the intensities of some of these apps, and if you look at these guys, they're all far less than the intensities we support on the architecture, and they all have problems. So let me talk quickly now about breaking this third wall. And there's 2 steps to breaking this locality wall. If memory bandwidth is the issue, one thing you might do is place the compute near the memory and essentially make smart memory. And then if scaling is the issue because of coherency and traffic, you want to move the computation and not the data. And so that's the idea behind migrational computing, where we move the site of a thread's execution when that thread wants to make a memory reference that's not local. And the rationale here is we want to make every memory reference local, so we avoid the cache coherency issue that kills us in a lot of these other problems. So here's a notional architecture. We'll have what we call a nodelet, which is our unit of parallelism. That's a chunk of memory, a memory channel, a smart memory front end, and one or more multi-threaded cores connected to this. And we're going to have a smart controller where we can do atomics in there. Our system will look like a whole bunch of these guys with all the memory in a global shared address space. And the migration happens when we have a thread, for example, executing here. It makes a reference to something that's not in this memory unit. The hardware hits it over the head, puts it to sleep, moves it over to a core in the right memory unit, wakes it up, and the thing proceeds as if it never knew it was on a different core. So there's no idea of where am I that the software has to be involved with. And these threads are free to spawn other threads and can spawn lightweight threads that can do local remote atomics, which turns out to be valuable. So there's a real system for this. I'm just going to advance through this. This is a real system that was built by my company, and there's a unit installed at Georgia Tech's Crunch Center, and the current cores are an FPGA, so they're running at about a 1/20th the performance of a classic core. And just very quickly, the kind of results we've seen when we ported SpMV to this kind of machine, we got scaling, which even in the worst case is positive, and in the best cases is really pretty good. And we didn't need any fancy partitioning or anything else. This is relatively simple-minded code, parallel code that just worked nicely. The Hogwild, a variant of that, again, we built an implementation of that, and even for the worst data set that was reported in the Hogwild paper, this thing called News 20, we saw excellent scalability and near perfect scalability for the other benchmarks. So that's also interesting. the Firehose with the migration, again, and this is really kind of ideal for, you think of taking a packet, you launch a thread, and it goes through and does the processing independent of the others. Here, the conventional system doesn't get much scaling as you move up. The EMU system, the multi-threaded system, gets good scaling, and in fact, for that box that we showed you, that about equaled the conventional system's performance, and this is with a core that's a 1/20th of that conventional core. So, looking forward very quickly, yeah. Was there a comment? Nope. Okay. I'm almost at the end here. Today, what we've got are plants. Our applications are changing to extreme locality sensitive. Physical locality events can dominate the time, particularly when you need to do it in software as we do today. And these migrating threads have real promise. They solve a lot of the problems. They remove the hardware coherency issues. They support rich atomics. And memory is a unit of parallelism, not a core. And so that leads us to what are we going to see next? Well, the world is going heterogeneous. In fact, there's a whole session, I think, later today on heterogeneous computing, where we're having all the kinds of different cores, and we're going to begin to introduce more and more computation into near memory, near caches, near local memories, and so on, all of which have to be tied together somehow. And so there's an issue here with how do you tie all those threads that are executing all over the place together. And I actually have a project with Georgia Tech to use these migrating threads as glues for the glue functions. And we're in the process of publications on that. So looking near term, what I think with a very effective future is we look at seas of 3D stacks where you've got memory, near memory processors, various kinds of accelerators and conventional cores on stacks, 3D stacks of things, with the bottom of the stack being a migrating thread core and I/O. And if you look at, now this says HMC, but you can think of this as any of the 3D stack memories that we use today. This is a system today, you've got high performance processors and bunches of stacks. What I'm talking about is crossing out the stacks, replacing the memories by these hybrid heterogeneous stacks, and putting the processing on those stacks is basically the plant level processing, the kind of computing we do today, where you're stuck in a core next to the memory and you don't really move. And then when you need to glue it together, you glue it together by migrating threads that run around and trigger various activities. So migrating threads here is the glue for this. So let me also just mention very briefly, I think there's something beyond this Cambrian heterogeneity that we're seeing. If you look at cells and computing organisms, you've got a whole variety of things, quantum, neuromorphic, DNA, optical, and what have you coming along. And if you look at computational paradigms, there's a whole bunch of things that are also becoming important. Reversible, various forms of non-von Neumann computing, probabilistic computing, and so on. And all of these don't look at all like what we do today. So what's next? Well, the obvious, I mentioned at the beginning that what people now believe caused the Cambrian explosion was a growth in predators. I'm not sure what a predator in a computer architecture thread is, and I'm not sure I want to know. But anyway, that's what's next there. But if you look even further, this is from Spock from Star Trek. It's what we're going to see in the future is stuff that doesn't look like what we've seen in the past. And just as a shameless thread, shameless plug here, I've finished a book called The Zen of Exotic Computing, which talks about all these things. That'll be published in 2022. So that's that. These are my acknowledgments, and I'm free to answer questions.
Thank you very much for this inspiring talk. Unfortunately, I forgot to instruct people to send their questions to the chat while you are talking, so I didn't have any. Oh, there is a question. Okay, that's good. Yeah, question. You were talking about thread migration in heterogeneous systems. Can you comment on the programmability of such a system? Yeah, that's a good question.
Well, that's actually this research project I have with Georgia Tech is about. If you look at the transition between calling a remote function, and in fact, a lot of what we're doing is you have a function, a remote function that you want to do that's on some other node, essentially a plant computation, if you will. And if you look at what it takes to call that function, what you need to transfer operands and get results back again. What we're looking at are compiler techniques to help perform that, and also what are the semantics of that. In fact, we have a table in a paper that from a conference 2 or 3 years ago that identified maybe half a dozen different kinds of semantic transfers, quote unquote, that have to happen when you have a thread over here that wants to start a thread somewhere else to do a function and then get a return. And so there is software systems that do a lot of that now, and there are programming models that do that, but they all do that in software, and each one only does a subset of the kinds of features that you really need. And so that's, hopefully we'll have some nice results on that fairly soon.
Okay. So let me ask a question, but anyone else should feel free to put their questions into the chat if you have some. Well, you said that if some thread is accessing data which is not local but on a remote site or some different place in the system, then you migrate the thread to that other position. When do you do that? Do you do that immediately, or is there a kind of threshold that the number of accesses must exceed before you migrate?
No, the hardware that we have now does it immediately. If you execute an instruction that wants to reference data, and that data is determined not to be on the current nodelet, the hardware puts it to sleep and ships it out. And ships it out to the right node, and then it gets unpacked and it restarts and never knew it moved. And you compare that to what happens in a conventional core when you make a non-local reference. And this is what is one of the killers on the apps for the sparse systems today. You do that on a conventional core, and you've got all this coherency traffic that has to happen, and all that time that core back that made the request usually ends up going idle, waiting. So you can't do much with it until the result comes back again. And when you have a lot of that, and particularly a lot of coherency traffic that causes you to miss in various caches and go all the way up and all the way back down again, those delays are significant. And that's what kills the achievable intensity on current cores. When you migrate the whole state, you leave nothing behind. So the thread just moves, it's out of there, and that core can be used by other threads. All these cores are multi-threaded, so other threads pop in and start using the core without any performance loss.
Okay, but that brings up the second question that I had, like what type of cores do you use? So you could optimize a core to have a relatively small state, but if you take modern cores, then you end up with a number of bytes that you have to migrate to a different site.
That's exactly right. And in fact, we chose the state for our core to be about the size of a cache line. 128, 64, 128 bytes is not atypical for a state. And you don't drag along a lot of, we've in fact split the state in half. Half the state is, if you will, memory space dependent, half the state is really thread dependent. And you look at today's state, they have a modern core, Xeon or something, it's all meshed together. Well, we separated those two pieces out. So the only part of the state that moves is the part of the state that's required to do the computation. Basically, program counter and some registers.
Mm-hmm. Don't you have any trouble with cold caches on the new site? If then the code is not or has not been accessed, and then you need some cache filling?
There are code. There's a copy of the code at each site, and there is a code cache, a local instruction cache at each site. But in fact, the original system. So today we don't have that issue because there's a copy of the code everywhere. The original system, the first system we built, this is like our third generation hardware. The original system actually included the code, small amounts of code with the thread. So, and in fact, the architecture was designed to be extremely small, and I could write interesting programs to do remote operations in 20 bits of programming. And it looks like a simple, I won't say accumulator machine, but it's akin to an accumulator machine that's designed to be very, very small in state.
Okay. Is there any publication on that architecture?
Yes, there is.
Okay, great.
The paper that is in the proceedings has a bunch of pointers to this.
Okay, very good. So we have another question that asks, how does that compare with data flow computations, where you also try to fit the machine to the needs of the application?
Yeah, well, data flow actually has a lot of similarities. Data flow, though, takes this idea of migration down to an even lower level, where an individual datum moves around, and but it doesn't. The datum itself doesn't include the instructions. There's no instruction pointer with the datum. If it gets to a function unit that's been programmed to wait for it, it will sit there until the matching operand arrives on the other side before triggering it to move on. And if you look at that's low-level hardware data flow. You look at software data flow. You usually have some sort of a buffer, and when all the operands arrive, you can then start the thread that starts with it, that's associated with that buffer. And that again, there's this notion that that buffer has to kind of sit still until all the things arrive. And sitting still means you're potentially utilizing resources. And in a sense, our threads never sit still. They're always in motion somewhere. They're either dead or in motion.
Thank you.
Okay, thank you. Are there any more questions? Feel free to raise your hand and ask the question yourself, or type it into the chat and I rephrase it for you. So your charts showed that the scalability of your system is very good. The speed up grows with the number of cores. Right. But I somehow had the impression that you pay some constant price for it. So I guess that an individual core is not as fast as what we are used to by, say, RISC-V cores.
Right, that's absolutely true, and that actually goes back to this business of the agile development. Our cores are done in FPGAs, and in fact, we're about to have the second generation FPGAs that are faster than the FPGAs we have now, and they're only running at 175 megahertz rather than 2 gigahertz, and they're only single issue cores. You know, there's no multi-issue. There's no out of order execution, what have you. They're single issue in order, but they are multi-threaded, heavily multi-threaded. So each core can have dozens to hundreds of threads on it, and that way we get really good core utilization, but the core itself is a really low clock rate, and that will change in time. But even with that, as I showed in the streaming example, we are near the same throughput as multiple Xeon-based cores with cores that, and the same number of cores with cores that are 20th the speed of those cores. So the ability to avoid the software is a tremendous performance increase, and we expect that when these things get eventually into an ASIC or a custom core, that performance will explode.
So is that a goal for the near future to put that into an ASIC?
Yes. Oh, okay. Yes, it is a goal.
Mm-hmm. We have another question?
Yeah, I have one more question. If I understood you right, the migration of the threads is at very low overhead, but
correct.
Still there is a little overhead. And what do you do if you have kind of ping pong problems? That means you have two memory references that are not local, and so your thread plays ping pong with these memory references.
Yeah, that actually happens, particularly when you've made a function call, and the call stack is on one node, and you're going back to do some processing, and you got to go back to get an argument from the call stack. And there's a couple of things that we've done there. One is the compiler tries to look at the operands and keep in registers rather than on a call stack operands that look like they're going to be used a lot. Secondly, let me see, what was I going to say? Secondly, the architecture includes in it the ability to say, I don't need these values right now, and they get tossed out of the thread state, and other values can be put into the thread state. So in a sense, we can shrink the size of the state as you go to keep the latency down, because there is a latency delay. Clearly, you got to move something from one point to the other, but that's only a one-way latency. And to go back to the example you had, where you had a ping pong effect with a conventional core, that core is going to be is sitting on one of the memories. It makes a remote reference. The time that it's dead is the time to go all the way out to the other memory and to come back. It's a two-way latency. Here, we not only don't leave anything behind at the first one, but it's only a one-way latency. So the latency of these things is reduced also. I'm not sure that's a full, but at least partial.
Okay, which opens up the question of how do you optimize the number of registers, for example, since you are increasing the locality by adding more registers, but then you increase also the number of data or the amount of data that you have to migrate. So there's a sweet point, and I guess that the sweet spot is depending on the application.
Yeah, that's true. We have a maximum number of registers, which is relatively limited. I think there's a maximum of like 20 registers that we can carry. But the compiler that we have that was based on LLVM, we went in and did a fair amount of register coloring to try to put the right registers in put the right arguments for a function call into the right registers. I should also mention that the programming environment for this is Silk and C++. And Silk, I don't know if any of you know Silk. It's basically, you add 3 constructs. The original Silk added 3 constructs to C. One was a prefix for functions, which said Silk spawn, which says execute this function as a separate thread if you can. And then there's another Silk sync, which basically says wait for all the children that are outstanding to complete before, basically a barrier before going on. And then we had a Silk for, which is the equivalent of a for all in OpenMP or something, where you can put together, you know, gang together a gang of threads to spawn a gang of threads to process something. The other thing we have is a pretty rich library, again, which has been tied into the compiler, of intrinsic operations, where we can do a lot of atomic operations that on a conventional machine are real nasty to do. You know, like a remote atomic add, where you've got to do on a conventional machine, you do a load link and a store and release or something like that, and do all kinds of software testing to do this. We do it all in hardware in a single instruction, and it's done. You're guaranteed that it's done atomically in the memory controller.
Okay. There's one more question that we got from the crowd. The question is, how do you optimize the number of migrations?
By programming, by observation, and it depends on the application. Actually, there are cases where the number of migrations doesn't matter. For example, in the streaming application, a migration, a datum, once it's taken by a thread and goes through the processing stream, it no longer cares. It doesn't care about. The only time it's ever going to go back is when it dies, when it's completed thing and it goes back to get another datum or something. And so in that case, the number of the only key consideration there is bandwidth on the links. And to date, so when you have lots of threads that are migrating at the same time, these links are rapid I/O links in our case, and you can get delays in getting across those things, but for the most part, if you do enough work, a few operations, half a dozen instructions on a core before you migrate again, the ratio of the time to do those instructions versus the ratio of the time to send the thread elsewhere is comparable. So the net effect is you don't see any delays.
Okay. I have one more question. Sorry for asking so many questions. If you take, for example, Graph 500, then one big issue here is how you organize the data in memory, because that can have a tremendous influence on the efficiency of your approach. So is there any way to analyze that beforehand and distribute data in a clever and a smart way?
Yeah, well, actually, that's been a lot of our thinking. In fact, the SpMV has the same issue. The sparse matrix vectored product has a similar kind of issue. Conventional implementations, there are all kinds of really fancy partitioning schemes to put different chunks of memory, different chunks of the matrix on different arrays. And one of the cases that my student did that I showed you actually involved hypergraph partitioning, a really expensive thing. And it did reduce the overhead of this communication by a factor, 90%. That turned out to be of almost no value on the EMU system. In fact, what's been interesting is what we've done with this architecture is kind of split the issue of data partitioning away from the issue of performance. So you write your code with a particular partitioning scheme, and that code stays the same regardless of how if you go back and change where the data is, as long as it's in this addressable memory space, it doesn't matter. So in other words, you separated out correctness from performance. Mm-hmm. And if you try to do that on a conventional machine, if you change how you partition the data, you rip up your software and start over again, because you got to figure out how things, where is something now. And on our system, it's the same code that you had before. You've just changed where the data is, and the code doesn't change, but your performance may change. So you can change how you partition data independent of the program to execute it. And to a large extent, you can then play with that partitioning. In fact, we're doing that right now with Graph 5. We're close to having some interesting numbers to actually announce on the Graph 500 data, and doing exactly that, looking at different partitioning schemes. And for the most part, we found simple is fine. Mm-hmm. The amount of gain you get is gain or loss you get is nowhere near what you see when you try to do the same thing on a normal distributed cluster.
Okay. Yeah, thank you very much. Are there more questions? So I see no raised hands and I don't see any message. I hope you'll be around in the break that follows, and I hope you'll be around in the evening gathering, what is noontime for you. Maybe you can make it to join us then.
Sure.
And then there's plenty of time to have a chat with you and discuss things any further on. Thank you very much for this interesting keynote. It was a big pleasure for me, at least. I hope for all the other attendees as well. And we hope to see you on the conference and have a chat with you. Thank you very much.
Sure thing.